presentation today features West Virginia's Basnettville Bridge Lateral Slide that took place this past August. We are pleased to welcome our presenters. They are Stephen Jarrell, Bridge Project Manager with the West Virginia DOT, Jeffrey Gola, Project Manager with Thrasher Engineering, and Jason Nelson, District 4 Construction Engineer with the West Virginia DOT. Stephen will also introduce Ahmed Mangi, QA/QC Unit Leader in the in-house design section of the West Virginia DOT, to say a few words to kick off the presentation. Stephen?
Good afternoon. I'd like to welcome everyone to the West Virginia Division of Highways presentation of the Basnettville Lateral Slide Project. My name is Stephen Jarrell. As previously stated, I'm a Structures Project Manager in our Engineering Division. Joining me today is Ahmed Mangi. He's our QA/QC Unit Leader from our Engineering Division. Jeff Gola, Bridge Designer from Thrasher Engineering, and Jason Nelson, the Construction Engineer from our District 4 office in Clarksburg, West Virginia. To start things off, Ahmed is going to speak about a few examples of our accelerated bridge construction projects from our past.
Thank you, Steve. Our first project is Honey Creek Bridge that was completed in 2006 at a construction cost of $2.6 million. This project was a design bid build project, which the contractor selected to use precast pier caps and abutments. The bridge was closed to traffic for 60 days during construction. Simple span for dead load and continuous for live load design allowed the contractor to complete the project on time. The second project is 16th Street Interchange Bridge that was completed in 2009 at a construction cost of $26 million. This project was also a design bid build project, and the contractor selected to construct precast pier caps and abutments. Stage construction was utilizing precast and cast-in-place deck options were specified in the contract plans, but the cast-in-place deck was selected by the contractor. Third project is Robin Hood Bridge that was completed in 2010 at a construction cost of $2.5 million. This project was a design bid build where precast pier caps and abutments were specified and constructed. This bridge was closed to traffic for a total of 70 days during construction. Simple span for dead load and continuous for live load design was also used on this project and allowed the contractor to complete the project on time. The third project is Dry Branch Bridge that was completed in 2013 at a construction cost of $1.7 million. This project was design bid build where precast abutments were specified. Bridge was closed to traffic for 2.5 months during summer break while the bridge was being replaced. Prefabricated beams, hybrid composite beams by John Hillman were specified in the contract documents. The fifth project is Rodney Station Bridge that was completed in early 2015 at a construction cost of $5.1 million. This project was design build where the contractor proposed to use precast deck tunnels. The project had to be constructed using stage construction, longitudinal post-tensioning of the deck tunnels, and semi-integral abutments were utilized in this rehabilitation project. The sixth project is Martin Luther King Bridge project that was completed in 2015 at a construction cost of $7.2 million. This project was a design bid build where full width precast deck panels, abutments, and wing walls were constructed. The bridge was closed to traffic for 2 months during construction. Longitudinal post-tensioning of deck panels and fully integral abutments were used for this 165-foot span. And now I'll pass it to Steve Jarrell.
What we're looking at here is a screenshot of a article that was written in Roads and Bridges magazine in November of 1988. As a little side note, I was actually a construction inspector on this project back a very, very long time ago when I had a lot more hair and it was less gray than what it is right now. This is the Polka Bridge replacement project. It was a 180-foot simple span through truss built in 1922, and the original plans called for a temporary 40-foot downstream. The contractor proposed using the existing bridge as a detour in lieu of building a temporary bridge. To accomplish that, he constructed a temporary pile bent, a simple connector span, and extended one of the abutments. The existing bridge was jacked 39 feet upstream under traffic in 9 hours. Cost savings of $115,000 on a $117 million project was realized. I guess I would like at this time to thank the good folks at Roads and Bridges for digging into their Wayback Machine and finding this article for me. On to the topic at hand, our Basnettville Bridge slide. This is a project in Marion County. It carries West Virginia 218 over Pawpaw Creek with an ADT of 2,400. The existing bridge is a 93-foot three-span built in 1954. Has a Y intersection with County Route 17 30 feet north from the end of the bridge and a Norfolk Southern crossing 65 feet south. A design study recommendation was a 100-foot simple span bridge with 30-foot clear width utilizing a downstream temporary. The sequence of construction for the alternate that was recommended in the design study involved installing temporary railroad crossings with warning lights and an impact to a 60-inch and two 24-inch culverts. There were utilities to be relocated, a water line, and overhead electrical, telephone, and cable. After that was accomplished, obviously we'd set up traffic control, install the detour road and temporary bridge, and then demolish the existing bridge. At this point, we can construct a new bridge on the existing alignment, return traffic to the new bridge, and remove the detour, as well as the temporary railroad crossing. It was estimated that we would have a duration of construction that would be approximately 8 months and a total project cost of $2.4 million. At this time, I'm going to turn it over to Jeff Gola with Thrasher Engineering.
Good afternoon. As Steve mentioned, we were hired to be tasked to design a set of construction plans for a lateral slide of the Basnettville Bridge. As Steve alluded to, the state had ventured into this before in the past, but it was actually the reverse. They were moving an old bridge for temporary purposes, and you weren't quite as concerned with that temporary bridge because we know it was not going to be permanent. This is a different scenario. Here we are trying to build a new bridge downstream and slide into a final location and be used hopefully for the next 50 to 100 years if we're fortunate. A little side note, the next few slides are going to pretty much show our logic, our method, and how we generate our construction plans to how it gets built. And a side note I mentioned is a couple weeks ago I was in a grade school teaching kids about bridges. We were actually making bridges with macaroni and marshmallows, and a common question comes up is, what do you do, Mr. Engineer? And my best explanation was, do you guys play with Legos? And most of them answered yes, and I was like, the directions you use to build those Legos? Yeah, I said, that's what I do. I put directions together. I put directions together to build a structure. So the next few slides are going to be my directions of how our theory, my methodology to produce a set of construction plans. For starters, we had to look at utilities. What utilities are we affecting? We had some water lines, we had a sewer line that we had to take care of, regardless of which situation we went to, whether ABC or the temporary bridge structure. The next thing is hey, how can we solve this job, make it a little bit more efficient, and save ourselves some costs? And one way to do that was to try to get the railroad out of it. We had a railroad nearby that we'd have to cross, that Steve alluded to. We had some utilities. We had a weird, unique Y intersection just upstation of this bridge that was very unique, all of which would have presented problems with a temporary structure and detour. So we were approached to do a ABC lateral slide. One of our first things we decided we had to do was we had to find a location for this temporary bridge, and we decided to make it downstream. It had a laydown area that was comfortable. It was a little bit more open and a little bit easier to access. So our first plan of action was to install temporary pile fence. Those would serve as our supports for our new structure in a temporary stage. We, in our plan, showed, or for our salesmen, we were selling them as steel piles. It'd be a platform for the new bridge to sit on and eventually slide to. We also had a theory of installing a steel pile on the upstream side of the existing bridge in line with the bearings of the proposed bridges so that we could have something to jack or pull against. So an anchor point. You have to have something to help pull you or push you to get you in the right place. The next thing we thought, hey, we're going to have this contractor right here driving piles for the temporary situation. Well, we go ahead and make this more efficient for the demo and the final shutdown. Let's go ahead and put the permanent pre-drilled piles in. So our theory was, let's do lane at time construction. Let's go in, pre-drill, and set the H-piles in the existing roadway. We used flaggers temporarily, and we backfilled that with stone until the bridge is ready to move. We're just trying to get ahead of the game. We're trying to see how can we minimize disturbance and save time once the bridge is closed and ready to be demoed. So we were trying to think, hey, we got a contractor in there doing piling. Let's go ahead and utilize him while he's there. Should help save the contractor time and money, but also achieve a little bit of a head start. The next thing we do is construct the new bridge parallel to our location of the existing bridge. And we do precast. We were planning on precasting the abutments, the wing walls, and the approach slabs. Now, this particular site, we could have built them on site. We can haul them in. We had a kind of open book on this. We could do it either way. But the goal was we were proposing them to be precast to save time, so that once the demo was done, we can move in, set the precast units, and start to slide. We utilize steel beams. Obviously, when you're sliding something, the less weight you can slide, the better off you are. That means lesser equipment, lesser jacks, maybe lesser pressures, and so forth. So we try to minimize the weight by using steel beams and so forth. The goal was to set the steel beams, cast the deck, pour the semi-integral closure pour, and pour the abutment and pour the parapets. So essentially, you'd have a bridge suspended in air downstream that looks like a completed bridge that we would eventually move over. I'll elaborate some more on the movement, but here was an example of a prefabricated abutment that we had in our plans that pretty much consists of a bridge seat that had a corrugated pipe that will allow the prefab abutment to slide over top of the piles. We use corrugated pipe because it lets there be a connection between the concrete and the pipe, and gives you some shear reinforcement and so forth that lets a better bond. The goal would be to set that over top of the piles and fill that cavity with a high-strength concrete. The next thing would be lateral slide. Before you can do a lateral slide, you've got to do some road closures. We have to plan out the detour. You can't just, this was not a location where you could just say no traffic allowed. There's businesses, there's schools, all this has to keep in operation. So we had to do a little task of going out there and finding a adequate detour road that could serve for a short period of time, in our case 5 days. So we had to do public meetings, set out media releases and so forth, and just make sure we set up early on the necessary traffic signs so no one's getting confused. We didn't want a bunch of people showing up to our bridge location and having to do a turnaround and leave. So we had to do all that stuff. Then one important thing we had in our plans is you have to install and test the slide equipment first. We definitely don't want to have the demo started and then realize on day number 2 that the sliding equipment's not working. So all that's going to do is just push the time out. So we wanted to go ahead and have in our documents and straight plans to test and slide the equipment before any demo was taking place, and that was the goal. So assuming that everything tests good, we're going to raise the new structure, place it on a slide or rollers, and we're going to close this bridge. You immediately start the demo. Once the demo is done, you start excavating out the pre-installed piles that we installed earlier on. Get the abutments, set them to grade, fill the cavities with high early strength concrete, and then start jacking the new bridge into position. Replace the sliders and rollers with the final elastomeric bearings. You know, one thing we had to do when we were tasked with this project was not only design the construction plans, we also had to be a little bit of a salesman. And these are pictures here. This is not the bridge that we actually slid, but these are some of the pictures that we used during our sales pitch. You know, we had help with the department, project manager, Steve, and so forth to try to sell this upper management that, hey, this is a way to do this. They've been doing it on other parts of the country. This is an ideal location. So we had to generate some pictures that showed our methodology, what actually they could see when they're out there to that site that day when the job is being partaken. Here's another picture that we were able to achieve that showed the bridge being moved over. You can see the bearing slides they used for this particular movement. Once again, we were just trying to illustrate that this has been done in other places and that we weren't reinventing the wheel, but we were doing something innovative that could be used on this particular bridge. As a salesman always does, whether you're buying a car or buying a house, you want to start comparing numbers. You want to compare things. You want to compare the alternative number one, which is a typical constructed detour temporary bridge versus this ABC construction. And so we broke it down to two sort of items: total construction, the construction cost, and then additional project costs. Additional project costs, you know, you have the engineering, you have the right-of-way, you have railroad utilities, all that stuff that the contractor really doesn't care about. He wants to know, he just wants to bid on the job. But as a management position, we've got to make sure that we're dotting all the I's and we have a good comparison to what is the savings, if any, from doing these two different options. As you can see in the construction phase, detour, we figured around a little under $300,000 to put the detour in. That counted the approaches and the bridge and so forth, and some piping that we had to do to get drainage situated around and so forth. The ABC approach, we figured around $269, and of course that detour also counted some of the traffic control and that kind of stuff, but also accounted for some of the temporary vents and some of the labor and equipment that may be needed to move this bridge over. So as you see, there's about $25,000 difference roughly in those numbers. As you see the total number between the two, there's not a huge difference in construction costs. So you could almost say they're an eye for an eye, but they're pretty close. But where you really see the savings is when you come down to the cost that you really don't see out in the construction part of it. Look at the railroad utilities. To deal with the railroad, as many of you guys may have done this before, it's not the easiest process. It can be a little bit time restraints on it. But we have to put a new crossing, a temporary crossing in. We'd have to put a temporary crossing in, possibly some additional signals for this job to take place if we use alternative number one. The utilities have been a little bit more relocation. We'd have to change the water line a little differently. We would have to adjust the sewer line a little bit more. So there's a huge increase, huge savings that we felt we would save in the railroad utility, just dealing with the topography and stuff that was in the area. We're looking at $245,000. So when you go down the bottom of the line, you look at alternative number one, total project cost 2.4, ABC 2.1. So I feel like, I think all you guys would, that's a pretty good selling point. You're saving, you know, a few $100,000. And I think that would be enticing to anybody when you still end up with the same product at the end of the day. You still end up with a 100-foot long bridge on the exact same alignment that you wanted to be on, and you achieved it. Total construction costs, as I mentioned, not bad at all. They're both very comparable. We did save some money in our alternative, but it was a little bit different there. So 1.5 construction cost. As you'll see in a future slides when Jason talks, he'll allude to what the final price was. 1.496 was our ABC. You'll see in a later slide from Jason that I believe the bids came in around 1.49. So as an engineer, that always makes you feel good because the prices were pretty close, and it made you feel like, okay, they interpreted the plans the way you wanted them to be interpreted. So it always makes you feel good when you see numbers close to what you estimated. So to wrap this up on my end, duration of construction, 5 to 6 months. Now, don't let that fool you. 5 to 6 months means the whole project time we felt to build the bridge to the side, get everything prepped. But for what the public would see, we only expected to have a 5-day road closure. So the normal Joe out there driving the street would only see a potential disruption, change in travel way of a 5-day road closure. So for 5 days, that'd be the only disturbance we feel like the public would really see as far as traveling wise, 5 days. Regardless if it took 6 months to build it or 8 months, they would truly only see 5 days. Our total project cost, as you saw on the previous slide, was $2.1. So that's pretty much how we developed our construction plans. As I said, they went to bid, and then, as you guys well know, once it goes to bid, it goes to construction, we turn it over to the district engineers, and right now I'm going to turn it over to Jason Nelson, District 4 construction engineer. He'll take you out.
All right, thank you, Jeff. So as they said, as Jeff mentioned there, I'm the construction engineer for District 4. My section oversaw the construction of the project. And just as an overview here, as we've already discussed, designers Thrasher Engineering. Contractor for the project was Kokosin Construction. And the bid amount did come back at $1,496,839.80. There were 3 bidders, and there was a span of less than $200,000 between the bids. So it appears that all 3 contractors, as Jeff alluded to, interpreted those plans, at least got the intent fairly close. Just a little bit of a timeline on the construction. There was a pre-bid meeting in April of 15. It was let for bid on May 19th of 2015, awarded on June 2nd. Notice proceed was given on June 16th of 15, and a pre-construction conference set up for the June 17th of 15. Now, our actual start did not occur until January 4th of 16, and the reason for that was a delay in a utility being relocated. And so our plan completion, we actually began after our plan completion of November 20th of 15 and had a revised completion of September 3rd of 16. Contractor completed the work substantially on August 19th of 16, so a few weeks early there from the revised set. Now, Jeff went through all of their methodology of how they designed this and decided to do what they did, and we had this nice, good-looking set of plans and a nice, good-looking plan of what to do with the bridge. And then when our contractor got a hold of it, they decided that they wanted to make a few changes, and they were good changes. But anyway, the plan concept was, as Jeff went over, pre-drill driven piles behind existing abutments while under traffic, precast abutment units, precast approach slabs and sleeper slabs, 5-day closure with an incentive-disincentive clause, existing bridge demo, bridge slide, place approaches, and open the traffic. To get into that ID clause a little bit more, we had a 5-day closure. We had to agree with the contractor on what was considered day 5, or the actual completion date of the slide and the closure. The incentive was based on no excuses payment, incentive of $12,000 a day prior to day 5 for a maximum of $60,000. There's a spec reference there that basically is saying that there be no allowances for weather or time extensions for the incentive. The disincentive payment was a penalty of $5,000 a day after day 5, no maximum. However, the time extensions would apply to that. The contractor substantially completed the project on day 4, and so received a $12,000 incentive. Now, to get into the VE change proposal,
bridge was shortened from 110 feet to 75 feet. 4 HP 14 by 102 bearing piles replaced the planned 6 14 by 73 piles. The abutment would now be cast in place. The approach and sleeper slabs would be cast in place with a higher concrete, since it would be done during the 5-day closure. That was a West Virginia Class B modified with a target of 3,000 PSI in 4 hours. Plate girders were now changed to rolled beams. The existing abutments would remain in place and eliminated the need for the reinforcing fill at the approaches. Shortened bridge eliminated need for the waterline relocation. All these changes resulted in a shared savings of just over $170,000. And with all changes, and as it stands right now, with the incentives and the VE pay, the total construction cost is just over $1.3 million. Now, just to kind of give an example of the differences here between of what got changed, we have a plan profile. You can see the existing abutments are removed, and the bridge is actually a little bit longer than what the existing bridge that was there. The VE actually moved those abutments inward, leaving the existing abutments in place. This is the plan abutment. I wanted to kind of show what happened with the abutment. This is kind of a unique thing that happened. Here was our plan abutment, 6 equally spaced piles, and it was changed to kind of a bridging structure, a bridging abutment with 2 piles on each end, which allowed access from the sides of the existing bridge and allowed no impact to the traveling public when those are being installed. To the right, you'll notice there's a notch installed on the abutment, and that is where that was the interface between the new abutment and the temporary vents to allow the bridge to transfer from the temporary to the permanent abutment. So I have a few pictures to go through here. This one's kind of showing the old bridge and those new permanent piles being installed. See some form work going up on the other side for these permanent abutments. And there are the completed abutments under the old structure and the beginnings of the temporary piling for the temporary vents being installed. There are the completed temporary supports just downstream of the new abutments. This is a picture of the day that they were setting beams. Shows a good view of how close we were to the existing bridge, and also the temporary, just under that timestamp there is one of the temporary support bearings that was used for holding the bridge while it was being built and while sliding. So now we go to bridge demolition. This is after the beams are removed, and I just thought this was an interesting picture in terms of our old abutment is still back there behind, retaining most of that embankment in behind there, but then also showing the how we had to work around the new abutment and not damage it. Just prior to this picture, there was a lot of protective cribbing that was on top of that abutment, protecting it from the demolition of the old structure above it. Just kind of a sequence of pictures. Here's a day of the slide showing the jacks in place with the wire strands in place, and everybody just waiting for the bridge to move. Kind of about halfway along. This probably would have been somewhere about an hour in. The total move took approximately 2 hours, and we see some workers there checking dimensions, making sure everything is coming up equal on both sides. and that is the bridge, I believe, the day after the move, and everything's in place, and we're starting to clean up and get things ready to get the approaches built. I put this picture in here just to show this was kind of one of our things that we learned on the construction end of this, is realizing that if we run into this this type of construction again and this limited space, how much congestion that there really is on the last day of getting this is the day that they got complete. This is somewhere probably about 2 or so in the afternoon, and we have every type of equipment that you can imagine shoved on that or around that bridge. Railroad equipment, a roller, asphalt, guardrail, everything, and we had a little dance with equipment there most of the afternoon. And here is our finished product, and what we have next is a short 45-second time lapse of just the 5-day closure period and the progress of tearing down the old bridge and sliding the new one in. You can kind of see workers there. The bridge slide happened very quickly. The majority of this work is, we were all focused on the slide, but a lot of the focus was the tie-in work, and that is something that we also learned to focus a little bit more on how to tile this in. The slide really actually went very smooth. It's a tie-in work that actually involves a lot more planning. And that's basically it. It's in place. I'm going to turn it back over to Steve.
We have a few lessons learned, probably a lot more lessons learned than we're even aware of at this point. Probably the single most important thing is that we feel that it's imperative that we all be open to new techniques. As you can see from the exercise that we've went through, we actually saved money by doing this, and that is not taking into consideration the user costs that are certainly incumbent on us all to pay attention to. Secondly, when you're going to do something different, you got to be prepared to sell it. We had to do that in this instance, and thanks to Jeff and Thrasher, they gave us all the ammunition that we needed, and we were fortunate that everything came back, and not only our initial bid was spot on, but then with the decisions that were made by Kokosing and District 4 and the division, we actually saved even more money than what we initially thought we would. Third thing is, while you're developing your plans, you need to be aware of the consequences of your material choices. We found out anecdotally after the fact that the one reason that the VE happened, not the only reason, but one reason that it happened, was the contractor was going to have potentially an issue getting plate girders, which we had specified in our plans, and by going to a shorter span, they were able to use roll beams, and that's something that certainly we go through that exercise in plan development, but when you're thinking along the lines of an ABC concept, it's probably more important than maybe even on a normal approach. And lastly, advanced planning, relocations, utility relocations, and more utility relocations. It didn't cost us really anything. Obviously, I'm sure Kokosing would have liked to have hit the ground running when the job was handed off to them. But in a different situation, this could have really been a bit of a disaster. And so that's one of our, to focus on any project that we have. It's an issue for us across the board, but it's really important on an ABC design concept. And with that, we'll open it up for questions.
Okay, thank you, Ahmed, Stephen, Jeff, and Jason, for your very interesting and informative presentation on ABC in West Virginia. Ben Bierman with FHWA will now moderate the Q&A session. Ben?
Okay, thanks, Mary Lou, and Steve, Jeffrey, Jason, Ahmed. Great job on the presentation. Folks, we received about, a little under 20 questions prior to the webinar, and I'm seeing the questions come in. I've got them grouped into basically 4 categories. Kind of go in this order. Implementation and procurement's the first category. The second is design. Of course, the third is construction. And the last one, we have some questions regarding cost. So we're just going to go ahead and get into this. And oh, before we do get started, Larry Buchart with Michael Baker and Chris Watson with Concosing Construction is going to join us in the Q&A session as well. Both were heavily involved with the project as well. So with that, let's go ahead and get started. We'll start with the implementation and procurement type question. So Ahmed, this probably one goes to you. A lot of contractors in other states are somewhat reluctant to consider accelerated bridge construction projects or accelerated bridge construction strategies. So what did West Virginia do to ensure that the slide was used and that it didn't get VE'd out?
We had a pre-construction meeting or a pre-bid meeting, which was mandatory. So that required any contractor that's bidding on the project to attend, and we went over the project technique and that.
Okay, and was that a mandatory pre-bid or was it optional?
It was a mandatory pre-bid, and
okay.
we had no VE allowed.
Oh, that'll solve that concern really quick. So you had 3 contractors that bid on the job. So in the mandatory pre-bid, did you have more contractors in the pre-bid meeting?
There was at least 5 contractors, and we received bids from 3 contractors, is my recollection.
Okay, great. All right, well, I'm seeing the questions come in, and they're really kind of focusing in on some of the questions related to construction more specifically. So we're going to kind of jump out of sequence and skip the ones on design for a little bit and hone in on those. So with the construction group questions, what types of bearings were used in the temporary condition and during the bridge slide?
We had, when we said the girders, as you showed the picture, we just had steel pedestals to support the bridge while we were casting the deck and the parapet and the abutment diaphragms. Then when we went to the slide, we just used a fabricated slide shoe. It was a steel slide shoe. And then once the bridge was in place, we removed those and installed the permanent bearings. So there were really no temporary bearings.
No temporary?
Those are just steel. What you can see there in that picture by the timestamp is just a steel pedestal.
Okay. And so how were your, how did you do with your predictions of the static and dynamic friction brakes as your predicted versus your actuals? Did the bridge move fairly well with what you all had anticipated, or were there any issues with the actual slide itself?
No, I mean the bridge slid significantly easier than we anticipated, but a lot of that was the calculations per the specifications required that I think it was we had to double all the forces. We had designed for 2 times everything, so our pulling force and our breakout force and all that were exaggerated because of the conservative requirements we had on our design. But we ended up probably about 7%-ish, right around there. It pulled very easily.
Okay, that's great. So were there any change orders required in the project? Did anything go differently than what was originally planned? And this is after the VE.
No,
Jason.
go ahead.
This is Jason. We, really there was no change orders that required or that changed things significantly other than the VE. The VE, even though we did have a plan note that said no VEs would be allowed, but it was specific to the bridge slide method. We felt when we submitted it to our management that what they were kind of VE and around the edges of the ABC method or around the ABC portion of this project, and but other than that change order, there were no other, with the exception of the time extension that we discussed on due to the utility delays.
Okay. So you all decided to build the abutments in front of the existing. So were there any issues or concerns or problems with placing the concrete and the re-steel to get that up underneath the existing bridge?
I mean, it was a little. Oh, go ahead.
No, you probably have a better answer than I do.
It was. It was tight under there, but we knew that when we proposed the change that it would be tight under there. We just felt that this conventional construction practice was a lot easier and cheaper, where we can kind of do a lot of this work without affecting the traveling public at all, and get all that done beforehand, not have to worry about precasting the abutment pieces and then using a large crane to set them and all that during our closure.
Okay, and then you shortened the bridge, I guess from a little around 100 feet down to 75. Did that impact the waterway opening? Were there any issues with the existing waterway permit to close that opening up a little bit more?
I'll answer that. No, Ben. Hydraulically, we didn't necessarily need the 110-foot span. The only reason we used the 110-foot span was so that we can build the abutments. We can install the piles behind the existing abutments, and we had to clear the existing substructure units, and that was the only reason.
Okay, great. And so there's a question here. It appeared that a train went by while the project was ongoing in the video. Did the railroad have any concerns with the use or with the construction activity adjacent to the active rail lines since they were in such close proximity?
They had their typical concerns about equipment that if equipment was on that side of the river or the creek that could potentially foul the track. We did have a railroad flagger on site while all work was being done, so he was able to inform the contractor if any trains were coming, although he did keep his work area well away from the railroad right away. They had their typical concerns. Contractor had to carry his our specified railroad insurance, and nothing any different than, I think they actually probably liked this method better because we didn't have a lot of tall equipment right in around their tracks.
Interesting. And so when the trains were going by, did you all have to stop, or could you continue to work on your activities independent of the train moving?
Yeah, those were independent. The train, they had enough clearance, and we didn't have any equipment on the other side of the tracks or anything, so work can just continue as usual.
Okay, great. So was there any instrumentation that was used to monitor the bridge during the bridge slide?
During the slide, we had our surveyor out there with robotic total station prisms mounted on the bridge. And after each stroke of the jack, he would take a quick scan, check, make sure it was moving uniformly, it wasn't getting out of tolerance or anything like that. We also had an as-built survey of it prior to any of the movement, and then again after it was moved to ensure it was in the right spot.
So did you have workers also checking the gaps and looking at the track line as well to see that things weren't getting out of whack, or did you just use the surveyor for all those activities, or to keep things in line? We
had workers on both tracks, just monitoring how far what moved laterally and its progression along the track, as well as
did it walk
equipment.
Okay.
A little bit, yeah.
Walk out a little bit on you, and would you just adjust it as you were moving along?
It just adjusted itself as it would stroke. It would kind of slide one way, and then once the jacks would stroke again, it would kind of just slide back and forth. It never got too far. It never got out of tolerance during the move. It just kind of slid up and down station a little bit as we went.
And were the jacks, they worked independent of one another, or were they hydraulically linked together?
They were hydraulically linked together.
Oh, wow. Okay. So were you getting equal pressures as you were moving them along, or did you see changes between the two?
There was changes between the two. It was a computerized, integrated system that worked together in unison at both jacks.
Okay. And it's sort of an add-on to this question. Was bracing installed between the beams to prevent differential movements of the beams, or were you just able to use, I guess this is an integral abutment, that provided enough stiffness for you all to jack against that?
We just used the bracing, the plan bracing, the permanent bracing that was already installed.
Oh, from the steel structures itself.
Yeah, that along with the integral abutment.
Okay, great. All right, so let me go into some of the questions that were related to the design here. So, did you need to build, or did you need to buy any additional right-of-way to build the structure next to the existing bridge?
No, it was, this is Jeff. No, we were fortunately only had to get TCE, temporary construction easement, but the final bridge would be in the exact same location as the old, so no permanent right-of-way was bought.
Okay, and so how close was the new bridge built adjacent to the existing bridge? You mentioned that you had to do a test move. How much gap did you give between the two structures?
I don't have that figure right in front of me, but I know it was somewhere in the 5 to 8 foot range.
Okay.
There was not much space at all between the two. But the finished product.
I was going to ask, was the test move just a couple feet, or was it something more extensive than that, like the 4 feet movement of, let's say, if you had 5 feet gap?
The test move was the requirement in the pre-move plan was 6 inches.
Okay, and then there was a question here. It's an integral bridge, correct?
It's a semi-integral abutment, yes.
Semi-integral, okay. And then there was a question regarding the concrete mix. It's 3,000 psi in 4 hours. That was your Class B higher early strength. Was there any cracking in the approach slab for that type of mix, or did you see any?
We haven't noticed any abnormal cracking. You always see a little bit more stress cracking in that high early mix, but nothing out of the ordinary.
Okay. And here's a question related to the environmental aspects. Were there any environmental considerations that came up during construction?
None that I'm aware of.
I'm sure the environmental folks would let you know if there was.
Yeah.
There was a question here regarding there's a power line in the picture. I guess this came up, Steve, when you were presenting, that showed up during the skinning of the bridge, and it looks like it was very low. Was there any conflict with the low-slung utility lines, or was that a temporary power line to this for the operations, for the contractor's operations? I don't know if you saw that.
I think the line that we might be talking about is a line that's actually, I can't recall if we relocated that one or not, but it was a line that's actually across the road from that Y intersection. It does in the picture appear to be a little bit closer, but it actually didn't interfere with the operations at all.
Okay, good. Now, y'all mentioned that, you know, there was an internal push to champion this method of construction to leadership within the state DOT. Did you also have to do the same, or go out to the public and say, look, we're going to come in and close your bridge down for 5 days? And if so, what was the public's feedback?
This is Steve. We actually didn't have any public meetings here. I mean, now there were public notifications that happened after the fact, but as far as you know, going to the public and saying, hey, we're gonna do this, we're gonna do this thing in 5 days, no, that wasn't part of the sales job, if you will.
Okay. And so there wasn't any like indication of, well, if you're going to slide it, you know, this is the best time of the year to do so, weekends versus weekdays and things of that nature?
Well, certainly our intent was to do this over, you know, to do the 5-day closure in the summertime when school is out. That was our aim, you know, from the beginning, of course.
And the detour is not significant on this project.
Okay, well that makes sense. So there was somewhat of a detour. So the 5-day closure, was that started during the week, or did it start on a weekend?
That was Sunday. I guess it would actually be a Monday morning at midnight, and went to the 5-day total would have gone then to Saturday morning at midnight.
Okay. There was a question that some clarification that was needed about how the abutment panels were installed. Were they installed under the existing bridge or just on the outside of the existing bridge?
On the outside of the existing bridge.
Okay, and that's, just I wanted to get that clarified as well. And then there was another question about stone fill placement in front of the abutments. Was that done? And if so, when was it done? Was it done prior to the lateral slide, or was that done afterwards?
Now there was
placement.
There,
Go ahead.
There was stone slope protection installed, and it was actually installed after the slide. I'm not really certain that that particular aspect, I believe they actually wanted to install that prior to, but there were a couple concerns. I know one was actually worker safety, walking back and forth while the bridge was moving, and the concern that someone might actually get twisted up in the rock. And but of course that made it pretty hard for them to place that. There was actually a good bit of hand and small equipment work to get that stone placed correctly after the slide.
Okay, good. And then there was a question regarding the cost of the lateral slide equipment. Was that separated in the bid tabs of the contract documents, or with the bids that you received, the 2.1 and then of course the VE, is that all inclusive of the lateral slide equipment in itself? Is there a separate cost item for that?
There was an item, there was a lump sum, or each item for a lateral slide, a prefabricated lateral slide. That would be anything incidental to that. So that we didn't break out the equipment, or that was the process. So we had a item for a lateral slide, which should cover the cost of the equipment, any structural, any engineering they had to have done to prove it worked, and so forth. So we broke it down that way. We broke it down as prefabricated bridge element lateral slide, which should account for any of their costs for equipment and so forth. Their method, their submittals, the temporary support, all inclusive of that temporary situation.
And was that spec'd out as a special provision almost, but it wasn't design specific? In other words, in the contract plans, did you all design the lateral slide setup, or did you let the contractor develop that system on their own?
We let the contractor to develop it. We presented the theory, but the contractor was responsible for their technique and means and method.
And maybe Chris, you can weigh in on this. Is that a preferred method from the contractor's perspective, or would you rather see something more prescriptive?
Well, no, we'd rather leave it open. That way we have the ability to use equipment we already own or material we already own. This actually was our third bridge slide that we had done in the past year or two. And we've had a lot of this equipment from other projects in the past that just worked really well for this. We had done a lot of research, just the way Thrasher did, looking at other states and other contractors and how they did things, and just kind of hodgepodge some stuff together we had in other projects and stuff we thought would work really well for this exact situation. And we're able to utilize a lot of stuff we had already owned. So, you know,
so I was going to say you answered the other question, which was, have you slid bridges before? And if you did, how did this one go relative to the ones you've done in the past?
The slides on all three went really well. This one was a lot smaller and a shorter distance than the other ones, so this one went really well, and plus we had a lot of lessons learned from the other two that we implemented in the design and the planning for this slide.
Okay, and then there was a question about labor management. Since a lot of this work was done in that 5-day period, what did you do with the management of your labor? Did they work in shifts, you know, to keep down the worker fatigue issue? And were there, on the site specific, and this is probably from the owner's perspective, were there contract limitations of when you could do this work activity? Did you get a 24 hours, 5 days opening, or was that time constrained to, say, not at nighttime hours, between evening, nighttime hours, so you're not keeping people awake surrounding the bridge?
We didn't have any time restrictions. We were allowed to work 24 hours a day during that period, and we did for, I think, the first 3 days. Maybe the first 3 days we worked 24 hours. Then as we got near the end, we got closer to where we needed to be, and I think we stayed home. We kept one of the crews home for a night there. But we had a day shift and a night shift crew that were working, so people were constantly there, but they were working normal shifts.
And so from the contractor's perspective, from the accelerated bridge construction, and using the lateral slide technique, is it a viable solution for you all? Is it one that presents challenges, or do you welcome the opportunity?
No, it's definitely challenging, but it's something we've done now, like I said, 3 times now, and we've got a lot of the pieces and parts to continue doing it successfully, and something we would like to continue to be able to do.
Okay, and so this question probably goes out to the owner, maybe Ahmed or Steve. All things being equal, would you take the lateral slide techniques and use them on future projects?
Yes, we like the way this one worked. We can't wait to try the next one.
Excellent. And what about accelerated bridge construction in general? Are you all actively pursuing that, or is it on a case-by-case basis? Or? Or is it something of avoidance in its entirety?
We're doing it on a case-by-case basis.
Okay, great. So with that, guys, we're up at the 10 after the hour there. So what we'll do is there's a few other questions that came in, and what we can do is post responses to those along with the videos and the PowerPoint presentations on the ABC UTC Center website. So with that, I'll pass the baton on to Mary Lou and ask her to give us a closeout. So Mary Lou.
Thank you again. Ahmed, Stephen, Jeff, Jason, Chris, and Larry, thank you so much for an excellent presentation and Q&A session. Thanks also to Ben for moderating the Q&A session. And thanks to each of you for your participation in today's webinar. The final count of registered sites today was 817. Please join us on December 29th for our next monthly webinar on the Knickerbocker Bridge project in Booth Bay, Maine. This concludes today's webinar.
Thank you.